Welcome back to ECE 501B. Homework number 3 is due on Monday. Our first exam is in a week. Next week at this time we will be having an exam. Review material is on D2L, and I hope to tell you a little bit about the process for exam number 1 at the beginning of this class. But if you've looked at previous exams, it's stated, I hope, on the front of those exams as far as what you are responsible for or what to expect. Then we will pick up where we left off last time, and we'll basically talk about or make a comment, one important note about maps and matrix representation, and that is that the basis that you're using impacts the numbers that you see in the vector or in the matrices, but it doesn't influence the linear transformation or the vector itself, the underlying properties. Then we will quickly go through addition, scalar multiplication, matrix multiplication, matrix vector product. We'll talk about invertible maps, which means that these maps are both injective and surjective. They're one-to-one and onto. We'll talk about what it means to have an isomorphic vector space, which means that they are similar. And then if we have our input vector space the same as our output vector space, we then call this linear map an operator. And most of the remaining part of the semester we will be working with operators. Here's the process for exam number 1. You will be allowed to bring in 2 sheets of notes, 8.5 by 11, front and back, for the first exam. You can bring in a graphing calculator. I'm not sure that will do you any good, but you can have it if that helps you feel comfortable in your chair. I'm all for comfort, especially you need to kind of have your head on straight for the exam so that you can be thinking clearly. Something to write with, but everything else is basically not available. No classmate, no textbook, no class notes, no phone, no computers, no asking your neighbor for help. That's the process for exam number 1. Then the structure for exam number 1. We have 75 minutes. There will be 5 problems. Expect at least one of those to be a proof. You may have to demonstrate or show or produce a counterexample, and that would involve using the appropriate definitions or propositions or theorems to justify your work. You may be asked to create or build something, and that might be a vector space or a subspace or a direct sum decomposition of a vector space. Or you might be asked to build basis vectors, or you might create some matrices or find the matrix representation of a linear map. You might ask, is this linear map injective, surjective, etc.? Those are the kinds of problems that you can expect to see on your exam, which will occur in 1 week. Questions on the process or structure? Yes?
For the propositions and theorems that might be used for the proof, do we need to know like the proposition number?
You don't have to. The question is, do we have to know the proposition number or the theorem number? No, not necessarily, but sometimes that's helpful, maybe. Sometimes I can think or remember numbers maybe better than I can remember other ways of encoding a theorem. So knowing, oh, this is proposition 323 or something. But no, you don't. You just have to sort of state what theorem you're referring to, or at least give some labeling on what theorem you're referring to so that it's clear why you're doing what you're doing. But having the exact number is not required, or labeling from the book. As I indicated, we wanted to start with an important note. So hopefully you can now type quickly or write quickly. But essentially this says that we talked about a point in space looking or being represented differently depending on the basis. So we could label this point in xy space 1, 1 as 1, 1 using the standard basis, or maybe we could label it as 1, 0 if one of our basis vectors was actually at a 45-degree line and of length the same as that length of the 1, 1 vector, or the square root of 2. So maps have an existence separate from their representation. That's what this important note is saying, just like vectors. And if you choose different bases, that changes the scalar numbers in the matrix or in the vector, but it really doesn't change the properties of that particular linear map, the truth or falsity of any statement about the map, nor any physically relevant numerical result. If you have a map, and I don't know if you've had a chance to look at, I think after the last class, after the video, I sat here until 9 or 10 o'clock that night and continued writing. It was kind of lonely, but I did it. Anyway, there are after-class notes at the bottom, and that now is hopefully helping you understand that even though this matrix representation of this linear map from point P1 to point Q1 may look completely different, it still gets you from the beginning point P1 to the ending point Q1. And it may do it in a much different way because of the basis vectors that you were using to try to represent those transformations. That's really what this is saying. And the end or the after class material from last time gives you an example of this important note or an illustration. I said we were going to breeze through. I guess I should have said we're going to scroll through these matrix operations. This shouldn't be at all a surprise. Matrix addition is just element-wise, but you obviously need your matrices to be compatible in dimension. You can't add a 2x3 matrix to a 6x6 matrix as a very extreme illustration. You have to have matrices of the same dimension or the same size, and if that's the case, then you can, if you're adding them, you can just add the elements at the appropriate location. Scalar multiplication simply scales each element in your matrix by that same factor. Those two operations taken together allow us to create a new vector space. And that's what I'm going to start writing on now. So now let's say that we are using the above two operations. And these are really conventional matrix operations. Of addition and scalar multiplication applied to matrices we can in fact define a new vector space from those operations. And it might be called, let's say, mat or matrix M, comma n with the elements of that matrix coming from the field F. And this notation, this mat, comma M, N, F, is the set of all M by N matrices with elements in this field F. So now you can add these, you can do scalar multiplication on those matrices, and that now, those matrices form a vector space. What's the dimension of that vector space? Now you could sort of start to think about this and say, okay, well, I can make some sort of default matrices that look like rows or columns. I could let M or N be equal to 1, and I know what the dimension of those should be. So this should be consistent with that thought process. Meaning if you set M, the number of rows, to 1, now you have a row vector that has N elements in it. What's the dimension of that? Pardon? So now this, maybe I'm misleading you actually, but now if you had a row vector and you had a set of those, what's the dimension? It's 1, isn't it? Because if you now have one line or one vector, it's really only that one vector that you're playing with. You're just living in that particular dimension. So here, the dimension is actually the product. So it would be 1, well, I'm sorry. What did I just say? I have to take all of that back now, don't I? So this is now n-dimensional. I knew I was misleading myself. So now this is going to be, so I had it right to begin with, and then I was overthinking it. But this now takes mn numbers to specify, just like your n vector. It takes n numbers to specify. Let's say that we pick something a little bit more than just the default case. Let's say m is n. We have 2 rows and 3 columns. Then in terms of this vector space, we could think about that having basis vectors. Let's say sort of a standard basis vector might be v1 would look like that. And then if we wanted v2, I'm hoping that these panes show you how I'm cutting up that 2 by 3 matrix. Maybe v2 is like that. And now you can see that for this 2 by 3 matrix we could have a basis, a set of basis vectors, let's say this standard basis that has 6 vectors. Each of these is a vector, and we're using each of those to be a basis vector. So this we could just say etc. for representing an element or a vector in this particular vector space, MAT, MNF. Okay. So now let's keep going with these operations. We've talked about addition of matrices, scalar multiplication. Let's now talk about multiplication. And hopefully multiplication of matrices will be consistent with what you've grown up thinking. So using the matrix representation, of a linear map, let's see what that leads us to. So this is now matrix multiplication. In contrast to the scalar multiplication. As a note, let's say in the special case, where we have the following. Suppose we have a linear map T that is a linear map from the input vector space U, an output vector space V, and now let's say we have another map S, linear map, that's going to be mapping between an input space V and an output space W. Then the multiplication of the maps could be sensibly defined let's say as ST operating on a vector V is the same or equivalent to S operating on TV. That's what we would expect, that if we formed the product of S and T and then applied that to V, that should give us the same result as applying S to the output of TV. And why I picked V, I have no idea. Let me pick U since we're starting in U. ST would be a matrix. Or right now it's really a linear map that enjoys what, if we now found the matrix representation of ST, it would be a matrix. So S alone is a linear map, and T alone is a linear map, and we have to, so those are generic. The question was S is a matrix and T is a matrix. I'm saying not yet. We haven't yet put them into a matrix representation. So we have linear maps, and we have matrix representations of those linear maps, but right now we're talking about the multiplication of the maps being consistent with what you're thinking about as matrix multiplication. So right now this is multiplication of the maps. ST applied to U is equivalent to STU. So now, and in general, we have something similar to what you would expect or know to be true for matrices. These maps do not commute. The map ST is not necessarily the same as the map TS. And now, how does this multiplication of maps work in terms of matrix representation? So how does this multiplication of maps, linear maps, work in terms of matrix representation? We would want what you're already sort of expecting. We would want the matrix representation of this map multiplication of S and T to be the same as the product of the matrix representation of S times the matrix representation of T. And in fact, that's proposition 43 in the book. And this multiplication works fine using the standard definition of matrix multiplication. And we're not going to cover matrix multiplication. I'm assuming we are comfortable with that, but you should review if necessary. What I would like to do, though, instead of going through, let's say, the strict definition of matrix multiplication, is illustrating a way to maybe think about what's happening when we are dealing with matrix multiplication, what that actually looks like. So, however, another way of thinking about matrix multiplication can be helpful. Let's look at an example. Suppose that I now have a matrix. Let's say it's 3 by 3. The first row is 1, 6, 4. The middle row is 5, 2, 5. And the third row is 7, 1, 3. And now we want to multiply that by a 3 by 5 matrix, where the columns of the second matrix are 1, 0, 0, 2, 0, 1, 0, minus 1, 0, 1, 1, 0, And 102. So here is A, and there's B. And if you did it the standard way in terms of multiplying, we would come back in a couple of hours and be done. But if you look at it a slightly different way, it's pretty quick to do this multiplication. And so what I would like to suggest is I'm going to now think of this matrix multiplication as taking the columns in B and using those columns to weight the columns in A. Meaning, B, the first column of B is really saying take the first column of A and scale it by 1. Take the second column and scale it by 0, and take the third column and scale it by 0. So really the result is just a copy of the first column of A, 157. So if you perform that multiplication, you would see that, oh, if you did it the standard way, you would say the first row times the first column, and you would see, oh, 1 times 1. You would see second row times the first column. Oh, there's a 5. Third row times the first column, and you'd pull off the 7. But in fact, another way of thinking of that is, oh, let's just look at B, the first column, and it's saying combine these columns of A in the following way. 1 times the first, 0 times the second, and 0 times the third. If we do the same thinking for the second column, that's saying take twice the first column and add it to the third column. So now I'm taking 2 times 1, or 2, plus 4, and I get a 6. Then I have a 10 plus 5, or a 15, and I have a 14 plus 3, or a 17, and I get 6, 15, 17 for my second column. Is that making any sense? No? So here I'm taking, well, here, let me do the third column next, and maybe it will start to make a little bit more sense, but maybe not. This one, using that strategy, is really saying just take and weight the first column with 0, weight the second column of A with -1, and weight the third column with 0, and add those up, meaning my result for this the third column in my result is just going to be the negation of the second column in A, or it will be -6, -2, -1. This is now the result of this guy really saying take the negative of second column of A. And if we go back now and say, well, what did we do with when we multiplied the second column in B with A? Well, we said we took 2 times the first column of A and added to that the third column. So now I have 2 plus 4. That's 6. I have 10 plus 5. That's 15. I have 14 plus 3. That's 17. And that's doing the same thing as first row, second column, second row, second column, third row, second. You're really doing the same strategy. If that's the case, what's the fourth column of my result? Just add the first 2 columns. And that's pretty quick to do. I can now just say 7, 7, 8. And what's the last column of my product going to be? It's going to be, I would probably double the third column and then add the first column is how I would do it. And say, okay, I have 8 plus 1, there's 9. I have 10 plus 5, or 15, and I have 6 plus 7, or 13. And there is now my product of an A with a B, it should be consistent. I should end up with a 3 by 5 result. And what did I do? Well, I used the columns of B to combine the columns in A. I could do just the opposite. If you like to work with rows, you could have said, but the reason I worked with columns here is my B matrix was sparser than my A matrix. I had more 0 entries in my second matrix. If my A matrix had more zeros in it, then I might use it to combine the rows of B. Because A, the first row, is really saying take 1 times the top row plus 6 times the second row plus 4 times the third row, and that's going to give me my first row of the product. But that's kind of a mess because A is so full. But you could do it that way. You could say, okay, the second row is going to be 5 times the first, and the first one's easy because I have 1, 0, 0. So I say 2 times the second and 5 times the third. Well, I just have really 5 times the first, and that gave me 5. But the others fill up a little bit more messy. What I'm suggesting is that's a way to think about matrix multiplication. If you now are saying A times B, I hope thinking about this way as far as, oh, B is just linearly combining the columns of A. There's no way I can get anywhere other than what the combination, linear combination of these columns will put me. And if these columns are actually dependent on each other, I'm not going to introduce a new independent span by linearly combining those linearly dependent vectors. What I'm trying to suggest is that you can think of matrix multiplication as combining columns, and this would be of the first matrix, or combining rows, and this would be of B, depending on which of those two matrices might be easier to think in terms of. Here, the sparsity in the second matrix, the B, sort of makes me want to do columns, but a lot of times I can sort of combine columns more easily than rows anyway, even if it's full. How many have already used that strategy for multiplying matrices or had seen it? Is that something new to most of you? You've seen it before? Use calculator? Oh, well, you you want to be able to use your mind and to sort of see what's happening. So thinking about it that way gives you maybe a little bit more insight than just plugging numbers into your calculator. And you can sort of anticipate if you now ended up with a result over here that was somehow linearly independent from the columns of A, you know you keyed in a number wrong. All right. So now let's continue a little bit with the standard concepts of matrix multiplication. The standard matrix multiplication maintains the properties we want. and that is really compatibility. Given, if we have an A matrix that, let's say, is M by N, and B, a B matrix that's, and now I can't make a J very well, so I'm going to make it a capital J so you know what I'm writing. J by L. The product AB is only defined when the number of columns of A equals the number of rows of B. You can't form the matrix product AB unless you have compatibility of the A matrix and the B matrix. And that's equivalent to the requirement that the output space of one map must be the input space of the other map. And which is which? Which map's output space or matrix output space needs to be the same as the input space of the other. And this is where you can kind of see why you have to observe the ordering of matrices. They don't just commute naturally. Now, the output space of B is forming the input space, or going into the input space of A, in order for that product to be true or to be valid. 2, even when we might have compatibility, even when the multiplications are defined, in general, the matrix representation of T times the matrix representation of S is not the equal to the matrix representation of S times the matrix representation of T. So those matrix representations or the matrices may not commute. We can also work with vectors. For example, Proposition 52 in Chapter 3 says the following: given a linear map, T, mapping from V to W, and let's say there's a basis on V given by lowercase v's, and we'll say that that's n-dimensional. And let's say we now have a basis on W spanned by W1 through W sub m. Then if we have this matrix representation of TV, that will be a vector, but that better be the same or equal to the matrix representation of T times the matrix representation of V. That's a small v. So now little v, That's our vector. I'm trying to indicate that as a vector. And little v would be then represented by a linear combination of these basis vectors. And that's consistent with this matrix representation product. Let's now look at invertibility. A linear map T between input space V and output space W is said to be invertible if there exists a map S that goes from W to V such that the map ST is actually the identity map likewise TS is the identity map. So S, or a linear map T, is said to be invertible if there exists another map S that takes W back to V, and such that the map ST is the identity map and TS is also an identity map. Here's a definition. A map S such that ST is equal to I and TS is equal to I is the inverse of T. That's the definition of an inverse. If the inverse of T exists, then it is, or it's, unique, and we will actually just call it T inverse, and we give it the symbol T inverse. Now let's look at a proposition dealing with inverted linear maps that have an inverse. Proposition 356. A linear map is invertible if and only if that map, or it, is injective and surjective. I'll let you go to the book to see the formal proof, but we'll talk about this conceptually as far as why is this the case. So see Axler for a formal proof. But now let's actually examine this from a more intuitive direction. Let's examine proposition 356 intuitively. Suppose we have a linear map T and it's non-injective. An injective, now we're focusing on the N because it has something to do with the null space, this map. If T is a non-injective map, what does that mean? It has a non-trivial null space, which means the null space contains more than just the zero vector. So we have vectors that are non-zero that, when operated on by T, go to the zero vector in the output space. Well, that means that we could use those vectors, add them to other vectors in the input space, and produce a different, or I'm sorry, the same point in the output space from different input vectors. So, if T is non-injective, then multiple vectors in the input vector space V map to the same vector in W. Pictorially then, we have, let's say, V1 and V2. Let's say this is now T of V1, and this is T of V sub 2, and here's W1. How are V1 and V2 related? You could say something like V2 is V1 plus, let's say, U, where TU is 0. That's what we're using, right? So now T of V2 goes to the same place as T of V1. Now, if that's the case, if T is non-injective, we're really trying to show what? We're really trying to show that if we have an invertible map, then it has to be both injective and surjective. Now we're trying to sort of show, why does it have to be injective? Well, here's a case where it's non-injective, and what does that imply? That means if we had an inverse, it needs to be able to start at W1 and know to go to V1 or know to go to V2. How's that going to happen? Because we've assumed that linear maps have a unique output. And that's not the case if we tried to put on a map here to make it go to from W1 to V1 or to V2. How does it know? So I'm going to try to write that down now. But that's what I'm trying to make you think about. So here, remember, a linear map requires a unique output for a given input. That doesn't mean that the output has to be unique, but it just means that each input needs to go to a unique output. There's no way the inverse map, let's say S, that's a map from the output space to the input space V, can exist. since it would have to map a single vector, this W1, a single vector in W, to multiple vectors in the input vector space, or what we started as the input vector space V. And if it has if every linear map has a unique output, that's not going to happen. So it can't be, an invertible map has to be injective, is what that's supposed to be giving us the intuition on. Likewise, it has to be surjective. So let's look at what a non-surjective map would give us. If T, this linear map, is non-surjective, and this one's playing on R, which is the range space, and a surjective map means that we fill all of the output vector space. If T is non-surjective, then in fact, then there are vectors in the output vector space, vectors in W, which are not produced by T acting on vectors in the input space, which are not produced by T acting on vectors, or on the vectors of V. But now if we had an inverse map, but the inverse map of T, but the inverse map S, that's supposed to start with any vector in W and take us to V, what does it do with those vectors in W that we didn't map to with T? It doesn't know what to do with those. But the inverse map S would have to ignore those elements in W, or those vectors in W. But that's contrary to what a linear map does. It has to be able to operate on all vectors in the input space. But a map acts on all elements of a space. And here's sort of a picture of this non-surjective map. Here's V, and we take any point in V and map it through T, and we end up, let's say there, in W. This inner cloud, let's say, is the range of T. And we may now have other vectors in W that we didn't get to from T, or I say through T from V. But if now S was our inverse map, S would ignore those points, and how would it know? So that's kind of the argument for invertible maps have to be both injective and surjective. It doesn't make sense otherwise. Let's look at using some of our other concepts to get a feel on what these inverses look like or what they possess. We had one result that said no map to a lower dimension can be what? Injective. Which is corollary 23 in chapter 3. And if we wanted to, if we thought about the matrix representation of that linear map T, what would it look like dimensionally? It's not square, and now it's mapping to a lower dimension, which means that its output needs to be smaller than its input. The input is determined by the columns of that matrix, so this one is wide and, let's say, short. And this is now a non-injective map. That would be the matrix representation of a non-injective map. We also have the counterpart relative to being surjective. No map to a higher dimension can be surjective. And now this map is just the transpose of the last one, or standing on its other edge. It's now tall and thin. And this one is non-surjective. So if we combine those two, we can't be short and wide. We can't be tall and thin. What can we be? We have to be Goldilocks, right? We have to be just right in terms of dimension. So we see that inverses only exist for maps between spaces of equal dimensions. And now you've already answered this question. Here's the question. What does this conclusion mean in terms of matrix representation? What's our Goldilocks answer? Now the matrix is square. In order, it has to be at least square, right? It has to be more than that, but at least it has to be square. Pardon? What's more than that? I'm meaning it has to be injective and surjective. It has to be more than just some matrix that's square. It's not just an arbitrary matrix to be an invertible or correspond to an invertible map. So the answer, dimensionally, it has to be square. So the matrix representation must be square. The columns of this matrix representation of T, if we now said TV1, TV2, TVN, the columns of that matrix representation are these, the action of T on V1, the action of T on V2, but how do we represent those columns? What do those scalars mean, or what are those scalars doing? Columns of this matrix representation are these outputs expressed in terms of the basis of our output vector space, which are the W's. Let's say W1, W2, W sub n. So the matrix representation are the scalars that weight those. Each column in this matrix representation of T is a weighting on these columns consistent with giving us TV1 in the first column, TV2 in the second column, etc. So if that's the case, if these scalar numbers, and how many of these TVs do we have? N. So now, using this last result, this says that we have to have the same number of rows. That's how many scalars we have to combine these W's. M actually needs to be the same as N. So the same dimension is going to happen only if the columns equal the rows. And that's our square matrix. So only square matrices have an inverse. And we could have square matrices that don't have an inverse. And what does that mean? That means we have linear dependency among the rows and the columns of that square matrix. Question?
So is the invertibility of the matrix equivalent to the invertibility of the linear map?
So now the question was, are these the invertibility of the matrix representation? That will be consistent with the invertibility of the map. So if we have an invertible map, then the matrix representation of that linear map will be invertible.
That sentence that you just wrote, is that related, when you say only square matrices have an inverse, are you referring to the invertibility of the matrix?
Yes, so now this sentence is referring to the matrix representations. So now only square matrices have an inverse. Is that clear? That's only referring to the matrix representations. Let's look at this concept of isomorphic. And I know that one of the main reasons you took this class is so that you could learn some new words, right? Isomorphic. So two spaces are said to be isomorphic if there is an invertible linear map between spaces. Between the two spaces. Two isomorphic vector spaces have the same properties. So here's a theorem based on that definition of an isomorphic, or two spaces being isomorphic. Theorem 359. Two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. Proof. So how do we prove this if and only if? We have to do the conditional in both directions. So now let's just state that. Need to prove in both directions. So we need to assume A and then show B, and then assume B and then show A. So first, let's assume two vector spaces, V and W, and let's assume that they are isomorphic. So here, assume A. So assume V and W are isomorphic finite dimensional vector spaces. By definition of isomorphic, what did we say? We said two spaces are said to be isomorphic if there is an invertible linear map between the spaces. So now if we have two finite dimensional vector spaces that are isomorphic, by definition of isomorphic, this means there is an invertible map T that goes from T to W. And what do we know now about an invertible map? Or what does invertible mean? It needs to be injective and surjective. So invertible means, or implies, injective and surjective. And now what do we know? Well, no linear map is injective to a finite dimensional vector space of blank dimension. And now we have two choices, right? Smaller or larger. Which is it? So if we have an injective map that means it can't go to a bigger or smaller dimensioned space. So no linear map is injective to a smaller dimension. So now if we have V as our input vector space and W as our output vector space, what can we say about the dimension of V relative to the dimension of W? So now we've only said that it cannot go to a smaller, right? So now what does that say about V and W? So the input vector space has to be so now we want an injective map. An injective map takes what? A non-injective map looks like this, right? Wide and short. So what's an injective map going to look like? So now what's the dimensional relationship between V and W for something like this? How is the dimension of V related to the dimension of W? Is it this way or this way? Can you tell which? So we're not necessarily concluding equality just yet. The input vector space has to be less than or equal to the output vector space if it's going to be an injective map. Is that okay? So this is now that way. The input space, the dimension of the input space is less than or equal to the dimension of the output vector space. That's what we just said, I think, here. It's said a little weird, but here we're saying no linear map is injective to a finite dimensional vector space of smaller dimension. So W has to be bigger than V, at least. Okay? So now, no linear map, if we use the same sentence structure, no linear map is surjective to a finite dimensional vector space of blank dimension. So if we want a surjective map, that map needs to go not consistent with my sentence. No linear map is surjective to a finite dimensional vector space of higher dimension or larger, whatever you feel more comfortable saying. So what does that do for our dimensional relationship on W and V, where W is the output dimension and V is the input dimension? So now we're saying that this no linear map is surjective to a finite dimensional space of larger dimension. So this now, W, needs to be what? This has to be smaller than the dimension of our input vector space. So now if we combine those, if we start with the first one, we say dimension of V is less than or equal to the dimension of W, but based on the second one, that's less than or equal to the dimension of V. What does that say? This is where we conclude equality. If W is squeezed between the same thing, it has to equal what's on the left and the right.
It's injective and subjective, so it must be equal.
Yes, so now it's both. It's both injective and surjective, so that the input dimension is the same as the output dimension. That now is what? That's what we needed to show for the first part. We assumed isomorphic, we assumed A, and we've now shown that the dimensions are the same. After class, I'll be here until midnight or a little later. After class notes, we'll show the other direction. Okay? And that's to start with the dimensions the same and show that it's isomorphic.